Okay, so instead we're going to try to use those regularized methods, which attempt to minimize the volume of space that can be occupied by low energy regions. And there's those three types of architectures that I was talking about in sort of increasing levels of sophistication. So this is a joint embedding architecture, a simple one, which when the two encoders are identical is called a Siamese net. This is a predictive architecture, but it's deterministic. There is no latent variable in the predictor here. So deterministic JEPA. And this is the full JEPA where you have both encoding and a latent variable. And I have to say, we have a lot of experiments with this. We have a few with this. We have almost none with that.
Over here, you're assuming, on previous slide for the architectures in the right, you're assuming some sort of ordering on the X and Y or some modalities that will allow you to predict?
No, I'm not assuming anything. So if you want to train a system to understand the world by watching video, this would be a segment of the video, and that would be the next segment or the previous segment or frames in between or something like that. If you want to do image recognition, this would be two views of the same object or the same scene, through distortion, explicit distortion with the program, or through just the motion of the camera or different lighting conditions or motion of the object. If you want to do multimodal prediction, this would be video, this would be audio. You can imagine.
But it seems like from one more informative modality, you are trying to predict the other one. But
less informative.
Less informative, but
possibly, yeah. Or the other way around, actually.
Yeah. Maybe you don't know which one is more informative for a particular task, and you want to even understand or learn that automatically.
Yeah.
And maybe you want something which is kind of symmetric in all the modalities and does that.
Generally, what you want to do is predict the most informative from the least informative.
But for a particular task, you may not know it in advance.
You may not know in advance. You're right. You might symmetrize it. I want to try to do it both ways, and one of them is going to work better. Right? Or you might deliberately degrade the information in X by masking, by blurring, by noisifying, reducing resolution, whatever. I should say also that this could be spatial. So it could be that Y is an area in an image, and X is another area in the same image. So in this case, you do spatial cross prediction. So here's the interesting thing about that. Let's say, let's say I'm going to take one line in an image and plot the grade level or something like that. Okay, most images are mostly constant and have changes. Okay, pixels don't get negative, but it's all right. And then you ask the question, can I predict the value of a pixel from its neighbors? Which would be a kind of situation like this, where Y is a bunch of pixels minus the central pixel, and then X, sorry, it's the other way around. So Y is the central pixel, and then X is the surrounding pixels. Can I predict Y from X? And in images like this, if you train a linear predictor, so you have a linear encoder with a linear predictor, you try to predict the central pixel from the neighbors, what you get is basically a Gaussian filter. So you compute a weighted sum of the neighboring pixels with decaying weights, and that gives you a good prediction for what the value of the central pixel is, because images are mostly continuous, except when there is an edge. But most of the time they're continuous, so that's a good prediction. Then, if you want to extract information, which is the difference between the prediction and what actually occurs, then it would be the value of the pixel minus its predicted value. And because everything is linear, you can represent this as a filter, which will look like this. And in computer vision, this is called a Placian filter, or difference of Gaussians, or Mexican hat, colloquially. So, and in wavelet, you can have some similar arguments to come up with wavelets. So, the whole idea that, you know, a processing system should try to predict everything from everything else, and then basically propagate information about the difference between what's predicted and what actually occurs, is kind of a very powerful one. Again, in neuroscience, that's called predictive coding.
Just to make sure, for ImageNet, what was the nice data you had for ImageNet? What was the perturbation that was done exactly?
It's a large collection of different perturbations. It includes cropping, so you take the full ImageNet image, which is, you know, 224 by 224, 256 by 256. You take a window of it, and then you resize it to the full size, and that's one particular distortion. You can change the colors. You can blur it. You can, and then there's I don't know what else. There's like a list of like a dozen different things you can have images go through.
But also like physical, like change of, I mean, rotation of the image that are much more complicated things.
Right, so there are experiments that are being done about this right now, where you have data sets where you have multiple views of the same objects. Either, so it's generally done with synthesized 3D models, because, you know, it's very complicated to collect that data. But there are experiments along those lines. They're not, I mean, they're still sort of either being worked on or on archive, but not, you know, submitted, but not really kind of published.
Over here, if we think of the self-driving case, we are trying to predict the next frame. Amongst the whole footage of self-driving car, only a very few rare images might be worth predicting for the next state, right? How do you also have to maybe get rid of lots of frames which don't matter at all, and if we just pass all the footage, I think it will be super hard for this architecture, right? So how do you tackle that problem?
Well, so if you want to make training more efficient, what you should do is what happens to a lot of living things that learn, which is that when your prediction significantly diverges from what actually occurs, then you pay attention and you update your predictive model with that. And whenever things are predicted properly, you just essentially ignore it. So when things are completely predictable, things are boring. And then there is something surprising that occurs, so your predictive model, you know, basically was not good, and that's when you pay attention. And that's when you update your model, you learn, etc. And you could imagine doing, you know, attention, selective attention, to sort of accelerate learning this way. Okay, so how are we going to, what loss function are we going to use to train this? And the loss function will have to do a trade-off, choose a trade-off between three things. The trade-off is going to be make Sx and Sy maximally informative about their input data. And that's going to be a tough thing to do. Make the representation of Y maximally predictable from the representation of X, and those two things are not incompatible with each other. It's easier to make things predictable if they don't have much information in it, right? So you're going to have to find a trade-off between those. And then for whatever things you cannot predict, but are present in the representation, use a latent variable to pick up the slack. And one way you can do this is through a conceptual loss function that will maximize the information content of Sx, maximize the information content of Sy. The difficulty here is going to be how do we estimate information content? Minimize the prediction error using some divergence measure, d squared, something. And then regularize this latent variable, because we can have a collapse. We can have a collapse of this model in three different ways, or two different ways. One way the system can collapse is that Sy or Sx do not contain much information about Y. For example, they ignore X and Y, and they're constant. The energy is zero all the time, not a good model. That's a collapse. So that's why you want to maximize the information content of other representations. But the second collapse you can have is if Z is too informative. So if Z has the same dimension as Sy, whatever Sy comes out of this encoder, there's always going to be a value of Z that makes the prediction error 0. And so that's another form of collapse, which I talked about also before. So you need to basically minimize the information content of that variable through some sort of regularizer. Okay. So two types of regularizations essentially: information content of representations, which you want to maximize; information content of the latent, which you want to minimize; and then prediction error.
So don't you have like an issue that sometimes the relevant information and the irrelevant information is not in the same units? For example, if you have an image, you might have like thousands bits of entropy in the leaves, but only tens of bits of entropy in the thing that you actually care about. So how do you deal with that with this kind of a loss function?
Well, the leaves are unpredictable, so if they are represented here, your predictor will have a hard time.
But there could be like also some large thing that is a large entropy, but somehow not changing that much with time or something like that.
Well, then it's going to be predicted away by the previous layer, hopefully. Okay. If you imagine sort of a hierarchical version of this, where the previous layer.
Okay, when you only care about the things that the previous layer didn't succeed on.
Right.
Yes.
Okay, so it's been a bunch of methods that we proposed over the last 2 or 3 years. One is BYOL, which was probably one of the first. Well, it's not one of the first. There was a method based on this sort of maximal mutual information between representations. There is I think a 1992 Nature paper or Science paper by Sue Becker and Jeffrey Hinton. So the idea goes back a long time, but it was in a very kind of restricted situation. And then more recently, there was this thing that the authors themselves claimed they just stumbled on, which happened to do kind of a, if you really try to interpret it, some version of what I just described, but it's not entirely clear why it works. There's been actually a bunch of theoretical papers that try to explain why it works. I don't understand why it works. And then other methods, some of which I do not mention here, but one of them that came out of my group at the fair called Barlow Twins, which basically tries to maximize the mutual information between the two representations using a measure of cross-correlation between the two vectors. So basically, you take the sequence of vectors coming out of those two networks, and which have to be shared more or less. They don't have to, but it's better if they do. And you take those two matrices, which are the representation vectors over a batch of let's say 1,000 samples or so, and you measure the cross-correlation matrix between those vectors. You get a square matrix whose dimension is the dimension of the representation vector, and the loss function is a measure of distance of that matrix to the identity. So we try to make the cross-correlation matrix as close to possible as to the identity. And what it will do is that it will make the vectors that come out of those two networks as equal, if you want, up to a scale factor to each other, and it will also prevent them from going to 0 because the diagonal of the covariance matrix has to be 1. And then there is a sort of improved version of this called VicReg. So this is my favorite method at the moment. And that means variance, invariance, covariance regularization. Yeah, so this is what Barlow Twins does. So this is the covariance matrix of pairs of vectors coming from the two halves, and this is a normalized cross-correlation matrix that you're trying to make as close to as possible to the identity. So the cost function has 1 minus the diagonal term squared, and then the off-diagonal term squared. And then VicReg is like this. So VicReg is you take the code here, and let's ignore this for a moment. You have two terms in the cost. One term that says I want the variance of each component to be at least 1. So there is basically a hinge loss that says the standard deviation of each component of the representation vector has to be at least 1. If it's above 1, I'm not going to make you pay a price for it, but I want it to be at least 1, so that it prevents a very simple dimensional collapse where all the variables collapse to 0 and the outputs are constant. Right? So you prevent them from collapsing, and this is computed. The statistics is computed over a batch of typically 1,000, a couple thousand samples. And then simultaneously, you minimize the off-diagonal terms of the covariance matrix. Okay, so you say not only do the variables coming out need to have a unique standard deviation or variance, they also need to be decorrelated from each other. And so that's a way of, it's sort of half-assed way of maximizing the information content with some very, very strong assumptions about the distribution, which is that dependencies are linear and you know, dependency is captured by correlation, which is obviously false. You can have much more complex dependencies between groups of variables that are highly nonlinear, and so by maximizing this thing, you're not maximizing the information content. It's kind of a differentiable simple proxy for information, but the system can cheat if it wants to, and it does. And in fact, that's the role of this expander. So this thing, what it does is that you take this thing, and it's a neural net whose weights are trained, and what it does is that it expands the dimension. So whereas this could be 2,000 dimensions, this would be something like 8,000. And then you apply this criterion to those 8,000 dimensions. And the 8,000 may include the 2,000 directly without going through the nonlinear function. The idea behind this, which may or may not be correct, but that's intuition and experimentally it works, is that if you decorrelate a lot of nonlinear functions of a bunch of variables, you make them more independent. Okay, these are ideas that are connected with ICA, independent component analysis. You guys know what that is. There's not a very strong theoretical argument for it, I have to admit. It's just that experimentally it works well. And then for this, you can just use the squared error. And then for this regularization, I'll have a whole spiel on this. So
the expansion operation, this is frozen or trained?
Say again.
The expansion operation, is it frozen or trained?
It's trained.
It's trained.
We try to keep it fixed, and it doesn't work as well. And it's trained with the same criterion, which is back for you. Right, so the Big Rec paper was presented at ICLEAR. It's been on archive for a while because it got rejected a couple of times before it actually got accepted. And it works really well, so in the sense that, so there are simple experiments where you pre-train on ImageNet and then you fine-tune with a linear classifier on top and see what performance you get on ImageNet. And this is on par with, you know, many other methods. And it's more general in the sense that, so it works pretty well for transfer tasks, like for other tasks that you didn't pre-train on. And the big advantage is that it doesn't require things like sharing the weights between the two branches. They can be completely different. It doesn't require any kind of normalization or batch normalization or any kind of hack like stop gradient or predictor or whatever. But anyway, I don't want to bore you with details. Here's the cool thing that you can do with these things. And this is not a completely accurate diagram, but it's the thing that if you are in front of a prediction task, it might be possible to make accurate short-term prediction with a high level of information about the input. So the same way you can run Navier-Stokes solver and predict the flow of air or fluid around an airplane wing or something. If there is turbulences and chaotic behavior, the prediction will actually diverge from reality after a while. So accurate, precise models can do accurate short-term prediction, but in the long term, they diverge, particularly for chaotic systems. But also for any system for which you don't have complete information. So you're observing the world, but you don't have complete information about the state of the world. You only have the information that your sensors give you, and perhaps what you can recover from memory, but it's not complete. And so your prediction, after a while, is going to diverge from reality because you don't have complete information. But what you can do is go one level up in abstraction level. So now have a more abstract representation of the world that eliminates the leaves motion from the trees, eliminates the details of the turbulent eddies around the wing of an airplane, and have kind of a more, less complete but more qualitative, perhaps, description of the world. And this one allows you to make longer-term predictions. So if I want to go from, if I want to walk from here to the village, I can tell it's going to take me about 40 minutes, but I can tell you the details of exactly what path I'm going to follow because that will depend on obstacles that are on the way, which I don't have information about. So this is something that says, if you want to do long-term prediction, you have to figure out what information you can ignore so that your long-term prediction is still useful and accurate. So that's called hierarchical JEPA, HJEPA. And again, these are not generative models. You're not predicting Y. They're not probabilistic because you cannot invert the encoder for Y. So you can't really turn this into the probability of the Gibbs distribution. That means there is no simple way to get a JEPA to produce a normalized distribution P over Y given X, right? So forget about that. It's hierarchical, and this diagram is incomplete in the sense that it would have to do what I just discussed, that the next level up actually just try to predict whatever the previous level could not predict, and that means it needs to be fed this, because this is the information that's missing from S1 of 0 to predict S1 of 1, so that needs to go to the next layer as well. There's sort of a missing arrow from here to here.
So we talk about maximizing the information content of two representations, but don't we need a normalized probability to define the units we measure the information? So how these two quantities are related and comparable?
Yeah, so if it depends how you measure information, okay? And there are measures of information that basically compute statistics over a bunch of samples. And you have to make some assumption about the form of the distribution to be able to maximize the information content. The assumption I'm making here is basically that the distribution is jointly Gaussian and even diagonal. I mean, not diagonal, but jointly Gaussian, right? So correlation measures dependencies. Okay. But in fact, it's false. We know it's not true. And in fact, that's a major impediment to a lot of those things. We don't have good ways of actually estimating information content, or at least not, good ways. Certainly not no good goal. Okay, so I discussed how you maximize the information content of the variables. If you have better ideas, I'm all ears. And then there is the problem of minimizing the information content of the latent variable. Okay, so again, because you can have a collapse if the latent variable is too informative, regardless of which architecture you use. So what we're going to do is to minimize the information content of this latent variable, we can do a number of different strategies. We can quantize it and discretize it. We can minimize the number of non-zero components if it's a continuous vector. We can minimize the Ly norm, which is nice because it's convex and differentiable, more or less. That's called sparse coding. We can do other things of this type. And the last one is that we can add noise to the z variable to make it not a deterministic vector, but sort of a blurry, hairy sphere or distribution. So let's talk about how classical learning procedures handle this information squeeze thing. So if you have an autoencoder, you need to regularize the information content of the latent variable. So let's take an example where, because otherwise your system will learn the identity function, which means the energy will be 0 for every input you feed it. So PCA does this by a very simple trick, which is you limit the dimension of the middle representation. So you have, let's say, a two-dimensional vector here, feed it through a linear function. So it's just a matrix that, or it's actually a vector. Compute the dot product of this two-dimensional vector by this vector. You get a one-dimensional representation, expand it back, reconstruct. Okay. And what this does is a projection on a linear subspace, and if you train this on a data set where the sample comes from this spiral, the projection function in the encoder basically projects on the principal axis of this data set, which happens to be this, and therefore the reconstruction error is going to be the square distance of any point to that one-dimensional plane, which is the principal subspace of PCA. And so the grayscale here represents the energy. Okay, you have zero energy on the principal axis, and the energy grows quadratically as you move away. So you don't have zero energy for everywhere because you limited the dimension of the representation. Here's the same thing, but now the encoders and decoders are neural nets with 2 layers, so you can do nonlinear stuff. And this is a particular experiment where the neural net figured out that this was kind of a low energy region, but then it gave relatively low energy to that part and low energy to that part, and that's a mistake. Okay, but that's what it did. Whether that's a better model than PCA or not, I'm not sure. Here is the energy you get from k-means. So k-means is a latent variable model, k-means clustering, where the energy function E of yz, so that you have a latent variable, and the latent variable goes through a decoder, and then you have a cost of reconstruction error. And in the case of k-means, the reconstruction error is just the square distance between the data vector and the product of the latent vector by a matrix whose columns are prototypes. And you constrain the z vector to be a one hot. Okay, so the z vector can only is all zeros except one component is 1. And so what it does is that it selects the column of W, the corresponding column in W, and when you do the zero temperature inference, so you try to find the z within the set of one hot vectors that minimizes the energy, the z kind of picks the prototype, the column of W that is closest to y. Okay, so it picks the prototype that is closest. It's very simple. You can view this as a latent variable model, where the latent variable is discrete and the decoder is linear. Okay, simplest thing. If you train k-means on this data set, what you get is, this is 20 prototypes. Each of this little kind of dark area is the center of is centered on a prototype. And so the energy is 0 at each of those 20 prototypes. And as you move away from any of those prototypes, the error grows quadratically until you get closer to another one, and then it goes down again. So it's the minimum of a bunch of quadratic balls that are centered on the prototypes. That's the energy function. And so you limit the volume of stuff that can take low energy here by simply limiting how many of those wells that you have. 20 in this case. K equal 20. You can have a soft version of this, which is gas mixture model, which I'm not going to go into. It's the same thing, except instead of minimizing, marginalized. Here's sparse coding. So sparse coding is kind of the same energy function, square reconstruction error, linear decoder, but then you have a regularizer, and this regularizer is the L1 norm of the z vector multiplied by some coefficient. Okay, so that regularizer is the one that limits the information content of the latent variable. It says, I want a latent variable, a latent vector that has the smallest possible number of non-zero coefficients, essentially. And when you apply this to the same little data set here, the sort of energy profile that you get is that each segment of that thing is approximated by a low-dimensional subspace, one-dimensional subspace in that case. The value can change as you move along, and the component that is being turned on in Z changes as you change regions. So you get the minimum of a bunch of quadratic balls that have one dimension where they can extend. In higher dimensions, there will be more dimensions that they can extend. So if you train a system like this on natural image patches, so the Ys are just a bunch of patches from natural images. This is the learning algorithm running, and each of those squares is a column of the W matrix. Okay, so basically what this does is, in the end, I'll show you the stable state. In the end, you can reconstruct any image patch by a linear combination of a small number of these guys. And they basically encode edges. Okay, because that's the most interesting thing that happened in images. If you apply this to NList, you get this. So you get like little pieces of strokes, and that indicates the fact that every digit can be reconstructed as a linear combination of a small number of strokes. That's replaced. Okay, there's one issue with this. Actually, I'm going to skip this whole thing about amortized inference for now. So amortized inference is the idea that instead of solving a minimization problem, you train a neural net to solve it for you. And there's a really nice review paper and tutorial by Brendan Amos at FAIR on that, which kind of reviews a lot of techniques to do this, and it's really cool. So I encourage you to, but I'm going to skip it. I'm going to skip this for now. Okay, so another way to regularize the latent variable is to make it fuzzy, make it stochastic. And this is where the math basically lines up with statistical physics. So the reconstruction energy you're going to get, so let's imagine that Z now is not a single point, but it's a distribution. So the expected reconstruction energy we're going to get is going to be the integral of the energy for various values of Z's that are taken from that distribution, which I'm going to call Q of Z given Y. And let's say that distribution Q of Z given Y is a uniform distribution in a small cube. Okay, so Z is a vector, and then every time I choose a value for Z, what I'm actually choosing is a little cube in the space of width S. And when I run through my training set, all of my Z's are actually turn out to be a uniform distribution in a cube of diameter R, okay, size R. Now, how much information do I get from any particular Z coming from that distribution? Given that the overall distribution of all the Z's is something like this, okay? And basically, it's how many of those little cubes I can fit in the big cube, and then I take the log of that, and that gives me how many bits of information I get from a particular Z, one of those distributions, right? So the information for each Z given a Y, where Z has this fuzziness about it, is log base 2, so if I want to measure in bits, of R divided by S, so the large size divided by the small size to the power D. Okay, this is how many small boxes I can fit in the big box, which is D log base 2 over S. So if I want to minimize the information content contained in Z, what I need to do is make the ratio R over S R over S as small as possible. Now, more generally, you may not have uniform distributions. It could be Gaussians or whatever, and you can go through the entire calculation of like what really is the information content, etc. So in the general case, the actual formula for the information content is basically the KR divergence between this Q distribution you're going to use that each Z is going to really be a representative of, and then the overall distribution of Z's on the entire training set. That measures, in bits, if you take log base 2, the amount of information that every sample Z with the fuzziness gives you about the actual value of Z. And so what if we maximize this? Well, obviously we get a very nice formula that you guys know about already, and that Francis actually talked about this morning. You get this thing that says, well, the expected energy is going to be the marginalized value of the energy with this distribution Q that I'm using for sampling the Z variable. And then, at the same time, this is the information content of that Z that I want to minimize. And I have a coefficient that modulates the trade-off between the two, which you can think of as the inverse temperature, and that's just the relative entropy of this Q distribution relative to P distribution. And as Francis talked about earlier, the Q distribution that minimizes this is the Gibbs distribution P of Z given Y, using the Gibbs formula, but it's generally intractable, so you don't do this. If you apply this to a Gaussian distribution, so you assume that every component of the Z variable is a Gaussian, you can actually compute analytically what the cross entropy is with a big Gaussian, and you get some formula, and this is basically what's used for what's called variational autoencoders. So a variational autoencoder is something that says, I want to make Z a Gaussian distribution with some width. I know they all come from some big Gaussian with univariance, let's say. And I'm going to use a neural net, an encoder, to predict the parameters of a Gaussian that is going to produce a distribution from which the Z will come. That encoder is going to compute the mean of the distribution as well as covariance matrix, which I'm going to assume is diagonal to save computation. And then my Z is going to come from that distribution, and what I'm going to have to do is maximize the covariance, or at least the ratio of that covariance to that covariance. Okay, so this is 1. I'm going to try to make this as close to 1 as possible, and then make the mean as close to the value of Z that makes the reconstruction error as small as possible, the minimum of the reconstruction error. Okay, and so that's an example of how you regularize a latent variable, the information content, using just an entropy measured over a batch or a training set. But here, in fact, you don't have any statistics over a training set. I mean, this one actually does indirectly, but you can measure the information content of a single sample because it comes from a distribution that is fuzzy. So mechanically, I like mechanical analogies. It means in the representation space, the latent representation space, every training sample is going to be some dot, okay? And we're going to make those dots fuzzy. Now, because they're fuzzy, they're going to overlap. And so if the system wants to minimize the reconstruction error, it's going to have to push all of those dots, all those fuzzy balls away from each other, so it doesn't make any confusion, because if you have 2 of those spheres that overlap, once in a while, you're going to get a code for this guy that is going to occur here, which the decoder is going to think is that. And so it's going to make reconstruction errors because of this, right? So what the system is going to do if you have fuzzy codes is that it's going to make the code vector fly away, which of course is not a good solution. So you have to tie that to the origin with springs, okay? And that's the other term, the regularizer. So basically what matters now is only the ratio of the length of that spring to the width of that bubble, okay? And that's this R over S, S over R, whatever. I mean, that's R, that's S. Okay. So I'm going to conclude with coming back to this autonomous AI architecture that I showed you in the first lecture, to kind of motivate this idea of self-supervised learning from prediction, the fact that you have to handle uncertainty in the world, the fact that if you want to handle uncertainty, there's 2 ways to do it, either through encoding what you're predicting to eliminate the irrelevant details, but also through a latent variable that needs to be regularized, and we saw how to do that, either through L1 and sparsity or through fuzzy regularization, like variational autoencoders. But okay, we're going to assemble this into an overall intelligent system. So how does this autonomous system work? The first way it works is it gets a percept from the world, run this to the perceptual encoder that basically extracts some representation of the state of the world. It could run this to its cost function, but that's not going to be very useful. And this is what is called mode 1, where the state of the world is going to go directly to some neural net that's going to predict an action on the world. Okay. And so this is the kind of mode you want to use for sort of reactive action that does not require any planning. And then there's mode 2, which I explained initially in the first lecture, where you use your predictive model of the world to predict what's going to happen if you take a particular course of actions. And then internally, you have a cost module that can compute the cost of the state that is predicted. And so you can adjust through optimal control. You can try to find a sequence of actions, perhaps using one of the methods that Francis talked about this morning, but those things are highly nonlinear, non-convex, blah, blah, blah. So perhaps with gradient descent or with dynamic programming or with other techniques, you can find a sequence of actions that will minimize the overall cost given the predictions that your world model produces. Okay, and this assumes basically a deterministic world, which of course is not true. So that's planning, it's classical planning and optimal control. That's called model predictive control. And then there is this thing that would allow the system to transfer something that the behavior that it produces through planning and turn it into a reactive policy. So I can run this planning thing and get an optimal sequence of actions that minimize my cost. And then what I can do is use those resulting optimal actions as targets for the actor, the policy network that just wants to produce an action directly from the state. Okay, so I take the state, run it through the network, and I train this network to minimize the divergence between whatever action it produces and the optimal action that was obtained through planning. So this is a way of turning what would be sort of a deliberate conscious planning operation into kind of a subconscious automatic reactive behavior.
So this is the mode 1 and mode 2 is supposed to correspond to system 1 and
system 2 from Daniel Kahneman. Yeah. The cost module, as I indicated in the first lecture, is a combination of two things. One is the intrinsic cost. So the intrinsic cost may have different modules that could be combined linearly in various ways, but they are immutable and they determine the nature of the agent. And then a trainable cost or a critic that has, again, different modules that can also be combined, but they are modulated by the task that the agent has to pay attention to at the moment. And those things are trained by predicting future values of that, okay? So the entire purpose of the agent is to take actions so as to put the world in a state around it that minimize the overall expected value of this intrinsic cost. And you can get help for that by training a cost function that predicts the long-term values of this intrinsic cost. Okay, and in reinforcement learning, that's called a critic. So one way you can use to train the critic is, I apologize for the mess here, is when the system is in a particular state, you record that state in some memory, an associative memory of some kind, and then you wait for a while. And then after a while, after you've taken a particular sequence of actions, you will measure a particular intrinsic cost. And what you're going to do is train the critic to predict the intrinsic cost that you eventually got. Okay, that's the way of critic. This is a very simplified explanation of how a critic can be trained. So going back to the hierarchical JPath, this one has the correct connection between the latent variable and the top predictor. We can use this hierarchical JPath for something called hierarchical planning. When I say we can, I should say we could, because we haven't actually tried. But basically no one knows how to solve this problem of hierarchical planning. So what is hierarchical planning? It means you observe the state of the world and you have some overall goal that you want to satisfy in the form of an objective function. And you have some sort of high-level, qualitative, abstract model of the world, right? I want to go from here to Paris. I need to, rent a car and drive, or I need to go to the train station, catch a train. So you can decompose like a high-level goal into kind of sub-goals. And then to go from here to the train station, I have to, walk down or call the taxi or whatever. And then, the lower level, I need to get out of this building. Lower level, I need to control all my muscles millisecond by millisecond to get out of the building and avoid all the obstacles. So a complex task is decomposed into simpler, shorter-term tasks. And this is what this idea does. So here, you plan a sequence of high-level actions like, going to the train station and catching a train. And you turn them into cost functions for the lower level. So going to the train station means what's my distance to the train station. And then, that's what predicts my position from the actions I take with my muscles, or whether I call the taxi or whatever, etc., all the way down. That's hierarchical planning. Now, the complication that you need to add to this is that the world is not deterministic. So in those predictors, there are latent variables that you cannot observe. There are things that may happen in the world that you can't measure, right? So, it could be that I call a taxi to get to the station and nobody answers, Okay, so there's a latent variable here, the binary latent variable, does the taxi answer or not, which will determine what action I can take, right? And I can't predict what this latent variable is in advance before I call. So I have to plan for different options, draw this latent variable from, a distribution perhaps, and explore multiple alternate scenarios that will depend on what those latent variables are. Now, if you imagine that this is not going to a train station, but it's playing chess, then the latent variable here is what the opponent is going to play. I don't know what the opponent is going to play, but for each move the opponent can make, I'll have a different resulting state of the world. And of course, the number of states of the world will grow exponentially as I go further in the future. So I'm going to have to use kind of heuristic strategies to figure out which part of that enormous tree am I going to explore. That's called a technique for this that's used by AlphaGo and all those things. It's called Monte Carlo tree search, where you explore only the branches of the trees that your system gives kind of low energy to, essentially. Okay, so that's a grand plan for the next 10 years to build autonomous intelligent systems. And the reason why I had this kind of ideas for a long time, but the reason why I wrote that review paper that I mentioned at the beginning, path towards autonomous machine intelligence, is because I think now we have the components to build those predictors using those JPA architectures with latent variable predictors. I didn't think we had the right tools before, so I didn't know how to build this. So some consequences of the use of this kind of model, self-supervised learning is kind of the central piece. I mean, this is where most learning takes place. We just observe how the world works, observe the world and figure out how the world works. That's how we build a world model. We can handle uncertainty in the prediction by either eliminating information through an encoder or through latent variables. And that has to be based on the energy-based framework, because I don't know how to do this with probabilistic modeling. This model would be kind of different from sort of classical deep learning system in the sense that the ability to do a search over optimal sequences of latent variables or actions, which are basically other types of latent variables, is a form of reasoning. So those systems are capable of reasoning, which is not the case for current AI systems. Now, here is an interesting hypothesis, which is that you need the system to be able to configure itself for a particular subtask. Okay, the system has kind of a limited capacity, and the world model is limited in some ways, and it needs to be able to configure itself to, for example, go to the train station as opposed to taking a train, or you're building a widget, you're trying to fix the Wi-Fi or whatever. You have some model of how Wi-Fi works, and you come up with some ideas about what you can connect with each other, and then you try and you fail, blah blah blah. But you have some mental model of what goes on, but your mental model is tuned for the situation at hand, and then you switch task, and your mental model changes. It has to be tuned for the situation that you're facing. And a good way of doing this for an intelligent system is not to have a separate world model for every situation you're facing, but to basically have a single one, a single world model that is configurable by what I call here the mysterious thing called configurator, which basically modulates the weights or the connection graph, or whatever you want, of the world model, perhaps of the perception system, perhaps of the actor, and certainly of the cost function. This guy basically sets a cost, an objective for the entire agent, the sub-objective that the agent has to focus on right now, and configures the world model for that situation. And then when that goal is fulfilled, it switches to another sub-goal and another world model adapted for that situation. And the hypothesis here is that we as humans and animals, we basically only have one of those engines in our head, or prefrontal cortex. We only have one world model, or maybe a couple. But essentially only one. And that would explain why, as humans, we can only focus on a single task at any one time. When our attention is focused on doing something, we can't do anything else, right? Or planning engine or simulation engine is configured for this task, and we can do subconscious tasks simultaneously, but we cannot do two conscious tasks simultaneously because we only have one world model engine. And it makes sense to have only one world model engine because you can share a lot of knowledge between different situations by having a single world model that you just reconfigure. Whereas if you have different models, you will have to train them. It's the same idea why having a single model that translates all languages is better than, or does speech recognition for all languages, is better than having separate models for each language or pair of language. That's kind of a crazy hypothesis, you know, if you believe me. And that's it. So prediction is the essence of intelligence, really, as physicists or engineers or people who write models of stuff. That's pretty obvious to us. Almost everything is learned. Hierarchical algebra with non-contrastive training is probably the thing that we should try to make work. Almost everything is run through self-supervised learning. Almost nothing is run through reinforcement or supervised learning because this is expensive. You have to take actions in the world that can kill you, so you don't want to do this. Or you need teachers. They're expensive. Intrinsic cost and the architecture drive behavior and determine what is wrong by the agent. And then, you know, crazy stuff. Emotions, you know, will intelligent machines have emotions? And the answer is absolutely yes, because emotions are barely more than an anticipation of outcome. You get scared where there is a lot of uncertainty about an outcome, and the uncertainty includes things that can kill you or hurt you. That's when you get scared. You get elated when you know that the outcome is going to be good, things like that. So you anticipate outcomes, and that creates emotions. There are other types of emotions that are more immediate, like pain and pleasure and stuff like that, but that's the intrinsic cost. The critic is more what generates emotions. So if we have autonomous intelligence that have cost functions and whose purpose is to take actions that minimize an objective, then they will have emotion because they will have to be able to predict future values of that cost, and that's what emotions are. So it's really inseparable from intelligence. It's not going to be like computer data that has an emotion chip they can turn off, right?
Isn't that our interpretation of the things?
Say again?
But isn't that our interpretation? Like, we are kind of putting our interpretation baggage on this thing, right? And saying these would be emotions, but
yeah,
like the machine does not really care anything about that.
It will care.
It would care about itself. I guess you don't have to have empathy, right? I mean, sociopaths are able to function in the world. So.
Okay. Yes. Okay, so according to this model, there is 3 ways you can be stupid. Okay, 4 ways actually.
Only.
Okay, the first way you can be stupid, so ignoring the configurator for now. The first way you can be stupid is that your world model is wrong. Okay, so whatever you predict is not what actually happens. The second way you can be stupid or antisocial is if your cost function is bad. So somehow your intrinsic cost does not actually predict, I mean your critic does not predict intrinsic cost, and you take actions that will actually eventually hurt you, or they will hurt, or they will contradict an intrinsic cost that, you know, measures empathy or things like that, right? We have an intrinsic cost as humans because we're a social animal that wants us to make other people happy, essentially. That's in human nature. And you know, some people might train a critic that basically overrides this term and that makes them antisocial. And then the third way you can be stupid is your actor, given that you have a world model and a cost, is not very good at finding a sequence of actions that minimize the cost, given the prediction. Okay? And then you have people who have all 3. The world model is wrong, their objective is antisocial, and they are completely ineffective at finding a sequence of actions that will actually arrive at the result they want. That's called double Trump. So reasoning is an extension of simulation, prediction, and planning. And perhaps consciousness exists because we only have one world model engine, and we need this configurator that oversees the overall function of the system to configure it for the right thing. And that gives us the illusion of consciousness. But that's very speculative.
So would you limit reasoning to planning? I mean,
that's the question. That's the question.
What else than what you're proposing? I mean, if you think about arithmetics, pure logic, I mean, there's this debate, I guess, in linguistics about
Sure.
Grammar, structure of the grammar.
That debate.
Is that?
Yeah.
Okay. Yes.
At least for the new generation.
Yeah.
Probably.
But in general, I mean,
yes.
there seem to be more than that. No.
Well, so like a SAT problem, which you've heard about from Mark, I suppose. Solving a SAT problem is a form of minimization with respect to latent variables. Right? You have a bunch of variables you observe, and then you have some that you don't, and you try to find the value of those that minimize some objective, which is the satisfiability of the formula. Inference in Bayesian nets or graphical models or factor graphs is the same thing. You observe some variables, and you try to figure out the value of the other ones that minimize in energy or maximize the likelihood, which is the same thing. So a lot of reasoning can be reduced to this. Now, one big question is, do you need explicit symbol manipulation for things like variable binding? So if you have a type of mathematical statement that says, x is divisible by 2 and x is divisible by 3, you have to sort of infer the value of this variable with kind of two statements that are sort of abstract. And you need an explicit mechanism that is present in sort of classical AI type reasoning in Prolog and things like that, or first order logic inference. Can you do this kind of stuff with this sort of architecture that does not have any explicit mechanism, symbol manipulation? And my hunch is no. A lot of people are absolutely adamant that it's yes. A lot of people who come from sort of the previous wave of AI that was logic based. I don't know really. There's been proposals along those dimensions. I'm kind of starting from, there's been sort of a constant also in my career, which is, if you follow sort of animal evolution, you start by figuring out like how learning can learn perception, okay, and then how learning can learn reasoning or word model prediction, and then you kind of work your way up. A cat can do all this. Doesn't speak. It can do arithmetics, or at least not with large numbers, but it can do all this. And so I'd be happy if within a few years we get to something that has the same type of common sense as a cat. A cat only has 800 million neurons. The current supercomputers that we have access to are big enough to actually have the same compute power as a cat brain, if you want. Human brain is about 100 times bigger.
They sleep less.
Huh?
They need to sleep less.
Yeah, that's right too. A dog is about twice as big, so it's 2 billion. Or a cockatoo is also 2 billion.
Maybe a related question on that, on the
Maybe we have this question
yes.
later.
We will be in trouble in the restaurant if we keep asking questions.
I'm here during lunch.